Oh, hello. I didn't see you there. Well, I'm a bit busy studying electron configurations for the chemistry final. I mean, with all of the studying of moles and equilibrium, it's really easy to forget that kind of stuff. Oh, you also have to study that? Well, that makes both of us. Might as well get started.
Now let's start by talking about what an electron shell is. An electron shell is not quite an object, but rather an idea of where an electron could end up going. Per electron shell, there are 2 electrons that can occupy the space. Now, electrons are like introverted emo kids, teeming with negative energy, but longing for beautiful protons. Now, because they want to be with this nucleus, they can occupy the same space. However, they do not want to be with each other, so they go all Scooby-Doo and spin opposite ways to avoid each other.
These electrons are able to go into 4 different types of orbitals. The first of these is the most simple, the s orbital, which is in the shape of a sphere. The s orbital only contains 1 electron shell, and because there can only be 2 electrons spinning in opposite directions per shell, the s orbital can only contain 2 electrons. Next is the p level, which actually has 3 shells, one in the x, the y, and the z axes. This makes it so that it's able to contain 6 electrons because it has those 3 shells. The next one is actually a very complex one because the shapes of it are hard to perceive in our 3-dimensional thinking minds. The D configuration has 5 different electron shells, making it be able to hold 10 different electrons. The F level is the most hard to perceive, and I'm not going to attempt to describe it, but all I can say is that the F orbital has 99 problems, but electron shells ain't one.
So now we've talked about the s, d, p, and f orbitals. Now, how do these exactly arrange into an atom? Well, we start with the principal energy levels. So, we'll start with level number 1. Now, this would have only 1 s. Because, as the levels go on, 1s is just the lowest that it can be. It doesn't have a p, d, or f. But this would continue on through the levels, stopping at 4. The second level would have 2s, and then there would also be 2p, because we are on the second level and there's 2 sublevels within it. Level number 3 would have 3s, 3p, and 3d. Now we'd continue on with this, 4s, 4p, 4d, 4f, and now we have our levels. So, now what you'd think is that the ascending levels would just go, the electrons would start on 1s, then 2s, 2p, and just keep on going throughout these levels until they reach the next. However, it actually takes a lot more energy to go into the higher levels than it does to go into the lower levels. So, sometimes, let's say, for 3D, it takes so much energy that it's actually easier for electrons to go into the 4s level. Now, how is this easier depicted? We use a staircase which would define exactly the levels that we would go with. This would continue on if we had drawn more levels. So it goes 1s, then 2s, and it goes from top to bottom across these different lines. So then it would be 2p, 3s, 3p, and instead of going to 3d, we go 4s, because it takes less energy to be able to go to those levels. Notice how for the F configuration, going to 6s, which is on the 6th level instead of the 4th, is a lot easier than going immediately to the 4f. With this newfound information, we are able to write the electron configurations for different elements at will. We'll start with nitrogen over here, which has an atomic number of 7. Now, a neutral atom of this would mean that it has 7 protons and 7 electrons. So, nitrogen, we will try to fill the different levels according to this. So, we'll start with the 1s sublevel because that one is the lowest energy state available. Now, because it has only one configuration, it can only hold 2 electrons. So we'll start with 1s2. We've only used 2 of the 7 electrons so far, so we'll have to go up another level. We'll go to 2s2 for the same reason, because it can only hold 2 electrons. Now we go to 2p. Now we've already used 4 of these electrons, leaving only 3 left. Because the p level is able to hold 6 electrons, we can just write the extra 3 electrons as a superscript right there. So it's 1s2, 2s2, 2p3. I'll write it bigger so that it's easier to see. Now we have potassium with an atomic number of 19. So we use the same rules as last time and write 1s2, 2s2, 2p6. So we've already used 10 electrons right there. Now, using the chart, we go to 3s2. That's 12 of them used. So that means that we have an extra 7 to go. Now, the chart makes us go to 3p6. However, because we're using the staircase method, instead of going to 3d1, we go to 4s1. There is also a shorthand method to shortening these different configurations as well. What we have been doing is the longhand method, where we write out every single orbital that exists for that atom. Now, to make it shorter, scientists have invented a way of shorthand where instead of using all of the different orbital configurations, we substitute earlier ones for noble gas. So for example, with potassium that we did earlier, over here, instead we would just use the configuration of argon and then just say 4s1, which would be a lot shorter to say. However, it does leave out the information that says which orbitals there are. But for a big element like uranium, let's just say that it's worth it. So we go to the periodic table, uranium's down here. If we go across, go up here, radon is the corresponding noble gas configuration. So in brackets we put the symbol of radon. And now we would write out the configurations that are left over. Well, that was some pretty good reviewing right there. We were able to review a lot about the electron clouds and all those models and stuff. Anyway, I gotta go now. Gotta get ready for that test a little bit more on my own. I will see you later. I gotta be more like an electron. I need to go my own way and can't be spinning the same direction as anyone else. This is my path, and I choose to take it. So, does that mean I'll get an A on the final? Sincerely, Electron Club. Don't you forget electrons. Don't you configure them wrong. Will you set the levels? SPDF subdivided, opposite spin, round, round, round. Will you do the longhand? Tedious but does the job. Shorthand shorter but harder to see.